So in the last video, we explained what the SP and D orbitals are, and I'll link that below if you want to go back and revise that first. But in this video, we're going to look at how you write the electron configurations for the first 36 elements to show which orbitals each electron is in. So we're going to start with an easy example, which is helium. So helium has an atomic number of 2. It is 2 protons and 2 electrons. And in year 11 and year 12, we'd write its electron arrangement as just 2. It is 2 electrons in the first shell. This year at level 3, what we do is we need to show which sublevel and orbital those electrons are in. So if we look at the bottom where it shows the energy levels of each sublevel, we can see that the S sublevel of the first shell is the lowest energy, and each box shows an orbital within that sublevel. So for the first shell, there is one S sublevel with the 1 orbital, and each orbital, represented as a box, can hold a maximum of 2 electrons. So in this case, the 2 electrons from helium would fill that first S sublevel. So for helium, we have 1s2 as the electron arrangement. The 1 shows that the electrons are in the first shell of the S orbital, holding 2 electrons in total, written as 1s2. And the 2 is written at the top in smaller letters. So next we'll look at a slightly more complicated example, which is silicon. So this has an atomic number of 14. So 14 electrons we need to account for in the atom, and its electron arrangement last year would have been written as 284, meaning 2 electrons in the first shell, 8 in the second, 4 in the third. And this year we're going to break it up to show where each of those electrons are found, so in which orbital they're found. So just like with helium, we start over here at the top left-hand corner, and again the previous video explains how to do this. And we just add the electrons. So the first 2 electrons will be added to the 1s orbital. So they're in the first shell, and there's 2 electrons. So they're both added to this orbital. Then we come down to the second shell. So in the second shell, there are 8 electrons we need to account for. The first 2 are found in the S orbital of the second shell, so it's 2s, and there's a total of 2 held in this orbital, so 2s2. Then we come across, and our next 6 electrons are going to be in the p orbitals. So they're in the second shell, the second p sublevel, and there are 2 that can be held in each orbital. So the electrons actually fill 1 in each orbital at a time. So 1, 2, 3, and then they come back and double up. 4, 5, 6. So there are 6 electrons in total held in the 2p orbitals. So we'd have 2p6. Then we come down to the third row, or the third shell. And so the first 2 on the left-hand side is the s orbitals. So we have 2 in the 3s orbital, or 3s2. So then we come across to the 3p orbitals, and this is the one that silicon is in. And so we have 2 electrons left. So the first one goes into the first 3p orbital, and then the second electron also goes into the 3p sublevel, but into its own orbital. So what we have then is 2 electrons in the 3p orbitals, or 3p2. So when we write the electron configuration, we have 1s2, 2s2, 2p6, 3s2, and then 3p2. And so we have accounted for our 14 electrons: 2, 4, 10, 12, 14. Right, the next one we'll look at is titanium. And this one here is found in our transition metals. So we're adding another layer because now we're looking at our 3D sublevel. So same thing, we need to account for this time 22 electrons. We're going to start here, 1, 2. The first shell, they go into the 1s orbital, and we have 2 electrons there. Then we have 2 more electrons, 1, 2, in the 2s orbital, so they come down here, 2s2. We have 6 electrons in the 2p orbitals, so all 3 orbitals are full, and we have 2p6. Then we have 2 electrons in the 3s orbital, so 3s2. 6 electrons in the 3p orbitals, so 3p6. And then we come down to our 4th row, or here we're at our 4th shell, but these d orbitals are part of that 3rd shell. So just like before, we start at the top and we move right and we add those electrons to the correct orbital. So this block here, or these 2 groups, the electrons are added to the s orbital. So we've got 4, 4th row, 4s, and there's 2 of them. So we have 4s2. And again, the s orbital, the 4s orbital, fills up before the 3d orbital because it's lower energy. But if you just follow the rule of adding to the right orbital as you go across, you get to the 4s orbital before you get to the 3d orbitals. So we have 4s2, and then when we get to the d orbital, we've got 1, 2. Here's titanium here. So there's 2 electrons in the 3d orbital. So we have 1, 2, 3d2. So here is our electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d2. Note here that I have written the 4s second, and the reason for that is it will help when it comes to writing the ions. So even though the 4s2 fills up first, I write the electrons in the 3rd shell together, and then I put the 4th shell at the end. So the last one is Krypton. Krypton is 36, and so that's the highest element that we look at. We don't go past 36, but we follow the exact same pattern. So the easiest way I find to do it is to start here and start adding the electrons. So each of these elements accounts for 1 electron. This is the s orbital, the p orbital, and the d orbitals. So we have in our first shell, we've got 2 blocks, or 2 electrons, 1s2, 2s2, 2p6, 3, 3rd shell, 3s2, 3p6, 4s2. We keep coming along. Here's our d. This is in the 3rd shell, so 3d10. And now we're back to our 4th shell, and it's our p orbital, and there are 6. 1, 2, 3, 4, 5, 6. So 4p6. When we write it, 1s2, 2s2, 2p6, Then we keep all the third shells together, 3s2, 3p6, 3d10, and then go on to the fourth shells, 4s2, 4p6. So this time the valence electrons are in the p orbitals of the fourth shell. So that's quite a lot to write by the time you get up to, the elements in their high 20s or 30s. There is a shortcut that you can use based on the group 18 elements and using brackets to simplify it. You don't have to simplify it. You can just stick with the full version of writing the whole thing out. Both will be marked correct in your exam. If you want to, you can use your group 18 elements as a shortcut. And we can use the shortcuts of helium in square brackets, got to be square, neon in square brackets, and argon in square brackets. So when we write helium, square brackets, what we're writing is 1s2, but we're doing it as a shortcut. Not much of a shortcut for helium, but for the others it is. Neon, when we write that in the square brackets, we're writing, essentially we're saying it's 1s2, 2s2, 2p6, but we're condensing that down to neon in brackets, and the same for argon. So if we use bromine as an example, so it's over here, it's element 35, and to write 1s2, 2s2, 2p6, it's going to take a fair amount of time. What we can do instead is we can say, all right, argon, that is the group 18 element before bromine, and it's important you pick the one before. So if I was doing sulfur, the previous group 18 element would be neon, and for bromine, the previous one is argon. So if we go backwards, the next one back is argon. And so when we look at bromine and argon, the first half of this is exactly the same, right up to 3p6. So what I can do is write for bromine, I can write argon in square brackets, or AR, just the symbol, not the full name, so just the symbol AR in square brackets. And then I can just write what is after AR. So we've got the 4s2, 3d10, and 1, 2, 3, 4, 5, 4p5. And so I can just write what comes after AR, which would be the 3d10, 4s2, 4p5. And you can do that for any of the elements. All right, so now we're going to look at those two exceptions to the rule, the copper and chromium. So we can't just move along the periodic table adding one electron to each orbital for each element, as we did previously. And that's because the 3D sublevel is more stable, so the atom is more stable when this sublevel is either completely full with 10 electrons or half filled with only 5 electrons. You don't need to explain why they don't quite follow the rules, why they're a little bit different, but just so you know, it's because the atom wants to be as stable as possible. And so to do that, it's better off when that 3D sublevel is either completely or half filled. So our first exception is copper, which is in the 3D sublevel. And if it followed the normal patterns, it would have, so we have AR square brackets come down, 4s2, 3d, 9. But here it's really close to having a full 3D sublevel. It's one off, so its electrons don't quite follow the pattern. Instead, what it does is it has 10 electrons in the 3D sublevel, because one of the electrons from the 4s sublevel actually jumps into the 3D sublevel. So it jumps into that last orbital. So instead of having 2 electrons in 4s, one of them jumps into a 3D orbital to fill this orbital. And so what it becomes is 3d10, 4s1. It now has a full 3D sublevel and it is more stable. And then our second exception is chromium. And so it's over here, it has 4 electrons in its 3D sublevel, and it only needs 1 more in that 3D sublevel to be half filled, where it will be more stable. So if it followed the pattern, we'd have square brackets AR, 4s2, 3d4. But just like with copper, one of the electrons moves from the 4s orbital into a 3d orbital to half fill it. So what we have is we'd have 1 electron in each of the 5 3d orbitals. So now each of these 5 orbitals have 1 electron, it's half filled, and the 4s orbital also is half filled with 1 electron. So it is 3d5, 4s1. And then the chromium becomes more stable. Copper and chromium don't follow the rules, and it's because they're one off having either a half filled or a full 3d orbital. And usually in the exam, you're asked to write 3 to 5 electron configurations for atoms and ions, and usually either copper or chromium pops up as an exception to see if you know those exceptions. So when we write the electron configurations for ions, if it's a positive ion, so a cation, the electrons come off in the opposite order to what they go on. So for example, 3p comes off before 3s comes off, because the electrons were added to the 3p orbital after the electrons were added to the 3s orbital. However, there is one exception to this, and again, it's that 3d orbital that behaves a little bit differently. So the 4s electrons are added to the 4s orbital before electrons are added to the 3d orbitals, but electrons are also removed from the 4s orbital before any electrons are moved from the 3d orbital. And the reason for that is, even though the 3d orbital is a higher energy generally, the 4s electrons are still in that 4th shell, so they come off first. So just remember, 4s goes on before 3d, but 4s comes off before 3d as well. So 4s is always first. You add the electrons to 4s first before 3d, but you also take the electrons out of the 4s orbital before you take any out of the 3d orbital. So let's look at manganese Mn3+. 3+ means it's lost 3 electrons. Its atomic number is 25, but because it's lost 3, it has 22 electrons. If we looked at the electron arrangement for the atom, we would see that it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. But we know that it's lost 3 electrons. So again, when we take those 3 electrons away, we need to take them away from the 4s orbital first. And that's why before I mentioned that you should write the 3rd shell sublevels together, so the 3s, 3p, and 3d orbitals together, and then write the 4s at the end. Because what that then means is you're just taking them from the end, and then once these are gone, then you can move to the next sublevel. So we need to take away 3. So we're going to take away 2 from the 4s2, because we always take away 4s first, and it's at the end. And then we still need to take away 1 more. And so we take 1 away from the 3d sublevel. So what we end up with is 3d4. We've lost both of the electrons in the 4s orbital and 1 of the electrons from 1 of the 3d orbitals. If it was a negative ion, so if it's gained electrons, then we just keep adding those electrons like we would if it was any element. So for example, if we had, let's say we had phosphorus 3-, it means it's gained 3 electrons. So we would need to add 3 more. And in this case, 1, 2, 3, they'd all be in the p orbital. So rather than having 1s2, 2s2, 2p6, 3s2, 3p3, we would now have 3p6 because it's added 3 more. So see if you can write the electron arrangement for the ion copper 2+. So you can write the electron arrangement for copper, and then because it's 2+, you'll need to take away 2, starting from the end and working backwards. Put your answer in the comments below, and I will let you know if you are right. In next week's lesson, we will be looking at the trends in the periodic table that you need to know for NCEA Level 3. So if you found this video useful, then please subscribe so that YouTube will notify you when this lesson is uploaded.